What's up, AP Calculus students? Mr. Ford here with another homework tutorial. This is for 4.2.2, and we are going to do all of the problems in this section, and this one might run a little long. I'm looking ahead at them, but all the problems here are really good, so I don't want to skip any of them. They're all worth doing, so that's why we're going to take our time with this one. This one might run a little longer, but let's just get into it. 456, we have G. He's trying to evaluate the integrals in parts A through C below. She already knows that the integral from 0 to x has this area function of 4x plus 1 over x plus 2. So we're going to use some thinking about integrals to help out with this set. We might use some space off to the side here. For question A, though, A is not going to be too tough because I already know that this chunk of it, the integral from 0 to 3, all we got to do here is plug in 3 into this equation. It's going to be 2 times whatever 4 times 3 plus 1 over 3 plus 2 is in this calculation. So that'll be 12 plus 1 on top is 13, 3 plus 2 is 5 down below, and so 26 over 5 would be the answer for that one. That's not too tough. But then you get a question like B, where you got to go kind of back in time one step. We do have a tool for doing that. We looked at it way back in section 4.1.3. Basically what we're going to do is we're going to take the function and we're going to slide it back one step. There was a rule we looked at way back where if I want to go the integral from a minus 1 to b minus 1, I have to go g of x plus 1 dx, basically is how this works. So what we're going to do is we're going to do the integral, we're going to treat this like it was the integral from 0 to 1. So I guess in this problem for question B, we're going to use that property. The integral from negative 1 to 0 of g of x dx is going to equal the integral from 0 to 1 of g of x plus 1, like that. We're going back in time. Actually, no, it's going to be x minus 1 because we are adding 1 to those things like that. That's it. So we're going to slide everything to the right, and we're basically sliding everything one step to the right. So what we're going to do here is we're going to just plug 1 in to our area function, but we're going to have to do an x plus 1. So our area function is this fraction, 4x plus 1. So now it's going to be 4 times x plus 1 over x plus 1 plus 2. We're taking that same area function that we did for the previous problem, but we're replacing the x's. Oh, they should be minus 1s. My fault. And all we're going to do is we're going to plug 1 in for x here and here, which is actually going to be really easy to do because if we plug in 1, we're just going to get zeros there. 4 times 0 plus 1 and 0 plus 2. So it's going to end up being 1 over 2, which that's the answer, 1/2, like that. Pretty cool. Question C is going to ask us to go back in time one step and then also forward 5 steps. But this is actually going to be pretty easy because we're just going to think about this as 2 separate integrals. We're going to think about this as the integral from negative 1 to 0 of g of m dm plus the integral from 0 to 5 of g of m dm. We already know the answer to the left part because we just did it in the previous problem. It's equal to 1/2. And we can easily get the right part because all we got to do is just plug 5 in to our area function from over there. So we're just going to get to that. It's going to be plus 4 times 5 plus 1 over 5 plus 2. This won't be a nice, easy fraction to combine, but it will be something we can do. So let's just think about it for a minute. We'll have 1/2. On the top, 4 times 5 is 20, and 20 plus 1 is 21. And on the bottom, 5 plus 2 is 7. So we'll think about that 1/2 as, instead, we'll think about it as, oh, geez, we have to combine both these. We'll think about the 1/2 as 7 over 14. And then we'll multiply by 2 on the second fraction, and we'll call it 42 over 14. And we'll add it together, and it will be 49 over 14, which those two both divide by 7, which would be 7 over 2. I feel like there's probably a better way. Oh, you know what I just realized? 21 over 7 is 3. It's 3 plus 1/2, 3.5. Oh, well. Oh, you know, you live and learn. Let's look at 457. Matteo and Ignacio want to calculate the integral from negative 2 to 5, negative 2 to negative 5 of f prime of x dx, where f is an even function. They know that the integral from 2 to 5 is negative 3. Matteo thinks it's negative 3. Ignacio thinks it's positive 3. Who's correct? So I'm going to need some space to draw on this question, so I'm going to move way over to the side here. 457. Let's think about this for a minute. If you're looking at that problem right there, we know it's an even function. Here's what we know about our equation. We know it's an even function, and we know the integral from 2 to 5 is worth, what was it, negative 3? Yeah, the integral from 2 to 5 is negative 3. So we know that there's some sort of function. It's got an area under the curve, or whatever. This area in the curve is negative 3. I don't know anything about this function. I just drew kind of a curve. I put it under the curve because it's negative 3, so I put it under the x-axis. We also know this is an even function. So whatever this graph does, I'm just going to kind of connect it to the axis there because I want to illustrate with even functions, they're symmetric to the y-axis. So the other curve looks like that. It's going to have the same basic shape on the other side. And it's also going to have the same area. So that's negative 3 also. Now, I think what's important to mention is that this is the integral from negative 5 to negative 2 of f of x dx. That's going to equal negative 3. And what's important is look at the order of the bounds there. We always go from left to right, negative 5 to negative 2. However, if you look back at the question, we're asked to do the integral from negative 2 to negative 5. So what we have to do is take that integral of negative 3 and switch it to be positive 3 because we got to change the order of the bounds. So this will equal the negative integral from negative 5 to negative 2 of f of x dx, which is negative 3, which is 3. So the person that's correct is going to be Ignacio. He's thought a little bit further ahead of the problem than Matteo. That's a good question, though. That's a really good visual explanation of what's happening here, is that we have the same area in both these chunks, negative 3, but you got to make the other one positive because you're going the other way with it. Okay, we got some bulky problems in 458, but we're just going to think about this one. Question A, a ferry crosses the bay so that its distance in miles is this function, d of t, 1 minus cosine t. What is the velocity at time t equals 1, pi, and 5 hours? And then explain what concepts of calculus you applied in order to solve this problem. So for question A, all we really got to do is find the velocity, d prime of t, which is actually pretty easy to do because the derivative of negative, we'll say the 1 is just going to be a 0, and the negative cosine is going to become a positive sign. So the derivative of that function is just positive sine of x. If the original function is 1 minus the cosine, I guess it's t, not x, so I should be a little more clear there. Now we need d prime of 1, which is the sine of 1, which I do not know. It's going to be a decimal, because remember, everything in AP Calc is done in radians. So, I don't know, 0.841. We need d prime of pi, which I do know. Sine of pi is 0. And we need d prime of 5, which is going to be the sine of 5, which is negative 0.9589. I'm just, calculator cam is, I'm staring at calculator cam and I'm not showing you what I'm looking at. I'm just asking the calculator what those sine values are. Get less blurry, baby. Go. Autofocus. Got it. There you are. So that's where those decimals are coming from. That's the first problem. As far as which concepts of calculus we used, all we did was take the derivative to find the velocity. That's it. Question B, when a cat chases a mouse, its velocity is measured in feet per second. V of t equals 3t. This is velocity. Sketch a graph and calculate the distance the cat ran in the first 5 seconds. And explain what concepts of calculus we used. So for part B, it appears we're going to go the other way. This time we're sketching a graph of 3t for the first 5 seconds. So here's 5 seconds. There's 5, 10, and 15. So there's 5, 15, and it's a pretty straight linear line right there. So this is a velocity graph, v of t. And so if we want distance, we got to find the area under the curve, which in this case would be your distance would be 1/2, or I guess d of 5. It'd be 1/2 times the base, which is 5, times the height, which is 15. 5 times 15 is 75. Okay, good. And so this is 75 over 2, which is 37.5. And I guess since the cat is running at feet per second, this would be feet right there. As far as which concepts of calculus we did, we went the other way. We used the area under the curve to find distance based on velocity. So here, we took d of t, we took its derivative to find v of t, which is d prime. Over here in question B, we knew the velocity, and we used the area under the curve to find the distance. We didn't really find an actual function. We just found the area at one specific spot, because going backwards is a little more difficult, but we'll be dealing with that a lot here in Chapter 4 and beyond. And I believe that's the answer to question 7. Question C, both A and B involve a distance and a velocity. However, each required a different method or approach. Describe the relationship between distance and velocity, mentioning the derivative and area under the curve. So here's the idea. We've flirted with this idea many times this year. The derivative of distance is velocity, and the area under the curve of the velocity is the distance. That's the relationship. Pretty soon we'll replace area under the curve with the phrase antiderivative, but we'll get there later on. Okay, let's keep going. Knew this one was going to go a little long, so we're about 10 minutes right now, which is fine. 4:59, while driving to work, Camille decided to keep track of the time and distance she traveled. Taking the data that she gathered, she found the function s to represent her distance as a function of time. So we have s of t right there. If her trip took 1 hour, how far did she drive? All we're looking for here is s of 1, because this is how far. That's a distance thing, and we have a function for that. So I'm just going to do this right off to the side. S of 1. And that's actually easy to plug in, because if you plug in a 1 into the function in those two places, you're just going to be doing negative 100 plus 150. So that's going to be 50. As far as her average velocity goes, let's just... I'm just going to go in the picture here for a minute. Let's just pretend that that point right there is the 1. S of 1 equals 50 right there. Average velocity is just going to be a slope of that secant line right there that connects those 2 points together. So really what we're looking for is we're going to do, I guess, the distance between, let's see. Okay, yeah, I'm just making sure this graph is in miles per hour. Sorry, I had kind of a brain fart. So all we really got to do is, if I want to write it all the way out for question B, I would do s of 1 minus s of 0 over 1 minus 0, which in this case is going to be incredibly easy to do because s of 0 is 0. So it's going to be 50 over 1, which is her average velocity is 50 miles per hour in that case. We're going to use her graphing calculator to determine her maximum velocity and how far into the trip she reached this speed. So this is going to happen all on the calculator. So here we go. The only thing I'm going to need before I go to the calculator actually is a velocity function, v of t. I'm looking for the maximum velocity. So the velocity function is negative 300t squared plus 300t. That's it. So I'm going to just throw that right into y1 on my graphing calculator, and we're just going to look for the maximum of that. That's all it's going to be. X squared plus 300x. There are other ways to do what we're about to do, but this is by far the fastest. So what we're going to do is, first of all, I got to really consider what my graph's going to look like here. I'm going to think about this for a minute. In my window, let's see. I know I want to start x at 0. I think 1 is all I really need to look at, honestly, because this parabola is going to have zeros at 0 and 1, so I'm going to call that. Let's call the scale 0.2. As far as the y goes, let's see. I'm trying to think what the maximum could possibly be here. I'm going to go from 0 to 300 and use a scale of maybe 50 to look at, and hopefully we'll see something. Yeah, that'll work. This is the velocity going on. Remember, that's 1 hour that was spanned out here, so I'm not too worried about this. All I'm going to do now is I'm going to find the maximum by using the calculate menu, second, calculate, and I'm going to do maximum right there. It's going to ask for 2 prompts, left bound and right bound, so all you got to do is click to the left a few clicks, and then push to the right a few clicks. It'll ask for a guess also, right kind of in the middle, and 0.5 and 75 appears to be that. So at t, I'm going to write this down on my get calculator out of the way. at t equals 0.5, in other words, half an hour, there was a maximum velocity. The max velocity was 75 miles per hour. Pretty good. That makes a little more sense, and that sounds like it works. Okay, question 460. Don't panic about this one. This is a really good example of what you actually will see on your AP Calc test. Change the following limit of a Riemann sum for the area under the curve into a integral expression, and then evaluate the sum with your graphing calculator. We'll be using the integral feature for this. So this is asking us for what how many we need to figure out a few things. We got to figure out what A and B are, like that. We got to think about what our original function was that's going to go in here, and it's going to be a variable dx right there. So let's just kind of ponder this for a moment. I'm kind of thinking about this for the first time too. These problems I always have to puzzle over for a little bit, so just give me a little bit of thinking time to really take in what's going on here. So if we really think about what's going on in this problem, I think what we've got is we've got length times width. That's going to be the key. There's your length, or I guess we should say there's your width. The 1 over n is the width of each rectangle, and this right here is the length of each rectangle, or I guess the height would be a better word for it, since that's our function. I believe that this is the function, x squared minus 3, or x to the third minus 4. Sorry, brain fart. That's going to be the actual thing that we're going to plug in here. I think that because each of these rectangles is represented by 1 over n, that's going to be the width of the rectangle, and so you take each one of those widths and make it x to the third minus 4 and plug it in. I believe the bounds of the rectangle are going to go from 0 to 5. I think that's based on, let me highlight that in green. I fully expect to just kind of take a shot at this problem, and then at the end of this video, I'll go back and look up the actual book answer, and we'll see if I'm 100% correct or not. But I think the translation of this problem is probably going to be something like that. X to the third minus 5 is actually going to go from 0 to 5. I'm pretty sure that's what it is. So at this stage, what we'll do is we'll grab the calculator and we'll plug it in and just see what the answer is, and that's less important than anything else. So we're going to go to alpha f2 and find our fn int, and we can just plug all the parts into this we need to. 0 to 5 of x to the third power minus 4 dx. And we'll get about 136.25, and we'll call this problem a day. And at the end of this video, I'll go back and look at that one in a little more detail because I don't want to spend too much more time on it. But other than that, I think that's going to be kind of the main goal of this. Anyway, question 61. If a function is differentiable at x equals c, does that guarantee that f of c exists? This is a really quick, easy one. No, it doesn't, and I'll give you an example right there. Oh, actually, I think it does. Sorry, I was thinking the other way around logically. If it's differentiable, here's what you got to know. If it's differentiable, a good word for differentiable is that it's going to be smooth. There are no sharp corners. There are no breaks in discontinuity, anything. The function actually must exist at that point, I think. There's no way to draw a real smooth curve and do anything that would cause f of c to not exist. F of c would not exist if there was an asymptote, if there was a hole. If f of c didn't exist, it wouldn't be continuous. And in order to be differentiable, you have to be continuous. So I think that's probably the best answer. If it's differentiable, then it's continuous. Because remember, in order to be differentiable, you have to be continuous first. Or, yeah. So being continuous is a subset of being differentiable. And being continuous means that the function has to exist. So I think this is a yes. Into the home stretch of this set of problems, we got about probably 10 minutes left in this video, I think. 462, write the equation of the tangent line of f of x equals sine of x at pi over 3. This is another one. You're going to see a problem like this pretty much on every homework set from now on. Let's keep practicing them as we go, too. You'll see them on a lot of quizzes and tests, too. I'm going to do the work over here on the side, 462. So we have an original problem, f of x is equal to sine of x. And we are kind of given this value of a equals pi over 3. So what we need to make the equation of a tangent line, we need to know what f of pi over 3 is. That's pretty easy, sine of pi over 3, which if I remember my unit circle correctly, I always got to think about where it is. The sign is going to be taller, so it's going to be the square root of 3 over 2. And we're also going to need to know what f prime of pi over 3 is, because we need to know the slope at that point. F prime of x, of course, is just the cosine of x. So f prime of pi over 3 is the cosine of pi over 3, which is going to be 1/2. And so putting all of this together, we know that at pi over 3, we get square root of 3 over 2, and the slope is 1/2. So putting it all together, we're going to have y minus f of pi over 3, which is the square root of 3 over 2, equals the slope, 1/2, times x minus pi over 3. And that is just coming from your good old point slope form from your Algebra 1 days. Y minus y1 equals the slope times x minus x1. We're just plugging those informations in. The AP Calc version of this is a little the same kind of idea, just a little more function notation thrown in. x1 gets replaced with a, and then you have f of a and f prime of a that go in there also. Those are the same ideas, though. Okay, next question. 463, differentiate. We got a bunch of differentiation problems here, so let's get to it. We have, this would be 7 times x to the 1/3 power. So the derivative of that, d dx, would be 7/3 times x to the negative 2/3 power, which could also be written as 7 on top, 2 times the cube root of x squared on bottom, but you don't really need to do all of that. Question B is already kind of in polynomial form, so not too tough to do. This would equal, a good language note would be that this is just saying what's the derivative of this expression. So the correct answer would be equals, because we're just going to differentiate and then write the answer down. Negative 21m to the negative 8th power minus 21m squared. I suppose if you wanted to put that negative 21 over m to the 8th, that would be a good thing. Unnecessary, though. C is really easy because k to the 0 power is just equal to 1. So the derivative of 1 equals 0. Nothing there. And then D, the main strategy here is to make sure you actually expand out that expression first. This is the derivative with respect to t of 6t squared plus 15t. And that would be 12t plus 15. There you go. Pretty straightforward. And of course, wouldn't be derivatives without some antiderivatives too. So let's think about general antiderivatives. Got to go backwards in time. Capital F prime of x. The key to these is really, with the polynomial ones, is to take x up a degree to x to the 5th power, and then think, okay, 5 times what would give me this 15 there? So that's got to be 3x to the 5th. For the next term, you would have x squared, and you got to put a 2 in front, because 2 times 2 would give you this 4 right there, and then minus 3x. And then, of course, don't forget your plus c. For question B, or capital F of x, this is going to be a pretty simple one. We'll leave that negative 2 right where it is. The derivative of sine is cosine, so this is negative 2 sine of x. Don't forget, plus c. And question C, capital F of x. One more time, we're going to take x to the 3rd and upgrade it to x to the 4th. And all we'd have to do is put a negative in front of that thing, because that would make it negative 4 plus the 10 times x plus the c. It's going to go right there. There you go. Take the derivative of those three, and you get right back to the originals. Hey, pretty cool. 25 minutes is not so bad, especially for some of the bulky problems that are in here. I want to take one more quick look at 460 before I end this video. So I'm actually over on another screen going to look up the actual textbook answer for this question and make sure I got the right idea before I leave you in this video, because I would hate to give you a wrong answer just to satisfy my own ego, of which I don't have anything. Just take a quick second. I appreciate you making it this far in the video. You're awesome, by the way. This is chapter 4, 0.2.2. Answers. Oh, I had the right idea. Just it's 1, not 0. That's the only thing I had wrong. Okay, cool. I was thinking that. I was thinking that would be a 1. So what I did wrong here in this problem, this is not correct. But the only thing that's actually, I shouldn't cross it off so violently. The only thing that's wrong is it's the integral from 1 to 5. That's what's going on there. It's the integral from 1 to 5. Yep. Yeah. Because I'm trying to think of a reason why. I'm really thrown off, I gotta be honest with you. I'm thrown off by this making infinity there and there. Integral from... But I suppose you would start with 1. 1 over... Oh yeah, I suppose, because it'd be 5n over n. It'd be 1 to 5. Okay. 1 to 5 of x to the third minus 4 dx. Yes. I like that answer quite a bit. Oh, you're not seeing what I'm seeing. There you go. I like this answer a little bit better. So if I go back and evaluate that same integral on the calculator, but change the 0 to a 1, looks like we'll have 140. That's a pretty more reasonable answer too, but that's it. Okay, cool. This video's already been long enough. You guys are awesome for making it here. You guys are great. Have a great day. I'll see you in the next video.